Morning, students. Myself, Vijay Shankar from EC Department, Chevrolet Engineering College. So today we are going to discuss about the concept of correlation. Already we discussed about the correlation and the cross correlation. So once again, we go. So what is a correlation and what are the different types of correlation? Now, the concept of correlation, the signals may be compared on the basis of similarity of waveforms. The signals may be compared on the basis of similarity of waveforms. Quantitatively, a comparison may be based upon the amount of component of one waveform contained, the amount of component of one waveform contained in the other waveform. So how far it is similar to the different signals. If x1 of t and x2 of t are the two waveforms, then the waveform x1 of t contain an amount c1 to x2 of t of that particular waveform x2 of t in interval t1 to t2, where c12 is equal to the integral t1 to t2 x1 of t x2 of t dt by the integral t1 to t2 x2 square of t dt. The magnitude of the integral in the numerator might be taken as an indication of a similarity. This point is very important, my students. So this is an equation. What we know already, the Cn is equal to integral t1 to t2 f of t x n of t dt whole divided by integral t1 to t2 xn square of t dt is orthogonality of approximation signal. In C12 equation, the magnitude of the integral is in the numerator might be taken as an indication of the similarity. If this integral vanishes, that is nothing but is equal to 0, then the two signals have no similarity over the interval t1 to t2. No similarity over the interval t1 to t2. Such signals are said to be orthogonal over this specified interval. The numerator is a 0. Definitely the denominator is energy signal. Energy is neither be created nor be destroyed. It is not at all equal to the 0. Only have to see that the numerator becomes the 0. The signal, such signals are said to be orthogonal over a specified interval, nothing but the t1 and t2. The integral t1 to t2 x1 of t dt forms the basis of comparison of the two signals. So mainly the correlation method, but it is a similarity. The two signals x1 of t and x2 of t over the interval of t1 and t2. So in general, in comparing the two signals over the interval minus infinite to infinite, so the test integral becomes minus infinite to the infinite x1 of t, x2 of t dt. Okay, my dear students. When we can say it is a similarity, however, there is a difficulty with the test integral, which can be illustrated with an example of a radar pulse. If here the figure shows the x1 of t and the x2 of t, shows a transmitted pulse and the received pulse. These are received pulse, my dear students, and this one is a transmitted pulse, which is delayed with respect to the transmitted pulse by the t seconds. There is a t seconds is difference here from 0 to t. We are transmitting the signal, sinusoidal signal at the transmitter side, and it receives at the receiver side after the delay of t seconds, capital T seconds. Obviously, the two waveforms are identical. Except that one is delayed with respect to the other. At the test integral minus infinite to infinite x1 of t, x2 of t dt yields 0 because the product x1 and x2 is 0 anywhere. This indicates that the two waveforms have no measure of similarity, which is obviously a wrong conclusion. Hence, in order to search for that, so when it is orthogonality, we are saying when the two signals are becomes a 0, we can say that it is orthogonal for the specified interval. Otherwise, have to search for the identicals, similarities between the two signals. What is that similarity? Similarity between the two waveforms, which we must shift one waveform with respect to the other by various amount, and see that whether a similarity exists for some amount of shift of one function with respect to the other. So the test integral modified as a minus infinite to infinite x1 of t, x2 of t minus tau. The tau is a delayed version into dt, where the tau is searching or scanning parameter. This integral is a function of tau, is known as a cross correlation function between x1 and x2, and it is denoted as R12 of tau. Okay, my dear friends. So that delay is nothing but either it is advanced and the delay function, shifting towards the right side and the shifting towards the left side, both are, it is a delays only. The sample of delay means after, advanced means this is before only. Follow my dear friends. It is immaterial whether we shift the function x1 of t by an amount of tau in the negative direction or the shift the x2 of t by the same amount in the positive direction. Okay, either in the negative direction, positive direction. So positive direction, we write it as a t minus tau. Negative direction, the shifting is a t plus tau. The values of the tau here, the t is equal to the tau samples, t minus of minus and the t minus plus tau. Okay, so R12 of tau becomes of x1 of t plus tau and x2 of t dt. Okay, my dear students. Thus, the correlation of two functions or signals or waveforms is a measure of similarity between those signals R12, the two signals. The x2 is delayed with the tau samples and x1 is advanced with the tau samples. But both the equations, both the waveforms or the signals or the waveforms is measure of similarity between those two signals only. Because the sinusoidal signal what we transmitted, it is delayed with the tau samples in the receiver side. Both have the similarity, or otherwise it is shifted towards left side with the tau samples, and comparing it, both are identical, similarities only. Okay, thus the correlation of two functions of a signals or waveforms is a measure of similarity between those signals. The correlation of two types, cross correlation and autocorrelation. It is a very important. The correlations are the two types, cross correlation and autocorrelation. The autocorrelation and cross correlation are defined separately for energy and the power signals. Okay, yesterday we already discussed about this one. Coming to the cross correlation, the cross correlation is between two different waveforms or two different signals, is a measure of similarity or match or relatedness or coherence between the one signal and the time delayed version of the other signal. Okay, correlation is nothing but either it is similarity or matching, or it is a relatedness or coherence So coherent between the two signals. And with the one signal, the other signal is a time delayed version of the other signals. This means the cross correlation between the two signals indicates how much one signal is related to the time delayed version of other signal. How much? It's nothing but it is 80% is similarity or the 90% of similarity. We can call it as a correlation. It's identical. How far it is identical. One signal to the other signal. One signal, the other signal is a delayed version of the original signal. Okay. And cross correlation of energy signals. Energy signals with the complex function. Say x1 of t and x2 star of t minus tau d. Or another equation is a negative direction also. The negative direction, the minus infinite to infinite, x1 of t plus tau, x2 star of t dt. So both in the cases we can take it as x2 and x2 star, the complex. If they are real, x1 of t, x2 of t minus tau, or x1 of t plus tau, x2 of t dt. It's a complex function of the cross correlation and the real function of the cross correlation equations. Okay. If x1 of t and x2 have the same some similarity, then the cross correlation R12 of tau will be some finite value over the range of tau. Also, if the integral minus t, integral minus infinite to infinite x1 of t, x2 star of t dt is equal to 0, when the tau is equal to 0, my students, it's nothing but equal to the energy signal. Okay. Then the two signals x1 of t and x2 of t are called orthogonal signals. Okay, the numerator becomes it is 0, definitely we can call it as orthogonal signal. That is a cross correlation of orthogonal signals is 0. Cross correlation for orthogonal signals is a 0. Okay. Now some of the properties, we have the three properties. R12 of tau is equal to R21 star of minus tau. So whenever the interchange of the 1 and the 2, the tau is becomes of minus tau, then only both are equal. So unlike the convolution, the cross correlation is not in general commutative. Okay, the R12 of tau is not equal to R21 of tau, my dear students. It is not a minus, it is a plus tau. And if R12 of 0 is equal to 0, means the tau is equal to 0, the cross correlation R12 of tau is equal to 0. Then the two signals are said to be orthogonal over the entire time interval. And the third one is the cross correlation of two energy signals corresponds to the multiplication of the Fourier transformation. Definitely, there's a multiplication of Fourier transformation. So because the time domain is a convolution, frequency domain function is a product only. The equation what we have, the cross correlation x1 of t and x2 of t minus tau dt. It is a correlation convolution equation. Okay. Now the periodic signals, for the periodic signals, the R12 of tau is becomes of 1 by t the integral of t. The equation is the same. x1 of t, x2 star of t minus tau dt, or R2 and 2 is the x2 of t, x1 star of t minus tau dt. Then the two signals x1 and x2 are orthogonal signal. That is the cross correlation orthogonal signals is a 0. And the 0, the tau is equal to 0, it becomes a 0, my dear students. The cross correlation of power signals. What is the difference? It is a limit t tends to infinite, 1 by t, the integral t. The remaining function is the same for energy and the power signals. It is a limited to the time period. Now the properties of cross correlation function for the power signals. So first one is the same thing what we have, Fourier transformation, x1 of omega and x2 star of omega, and tau is equal to 0. The cross correlation R12 of tau is also the 0. That is limit t tends to infinite 1 by t the integral t. And the third property is also similar, R12 of tau is equal to R21 star of minus tau. Unlike the convolution, the cross correlation is not commutative. Similar properties what we have in the energy, the power is also the same. So only the difference is the equation. It is a limit t tends to infinite 1 by t the integral t, or minus t by t the t by t. So one example we can see, one of the property only, that one. Through that, R12 of tau is equal to R21 star of minus tau. That is, the cross correlation exhibits conjugate symmetry. Cross correlation exhibits conjugate symmetry. We know the cross correlation of two signals, x1 and x2, is given as one signal, and the two signals we can take x1 and x2, and second signal is delayed and complex. R12 of tau is equal to integral minus infinite to infinite x1 of t, x2 star of t minus tau dt, and let the t minus tau is equal to n. Let t minus tau is equal to n minus 2. T minus tau is equal to n, where the t is equal to t minus tau in the second signal, assuming that n, what is the t? T is equal to n plus tau. N plus tau. And dt is equal to, tau is a constant, and apply the variable for the t and n. So R21 of tau is equal to, now it becomes of t as n plus tau, and n x2 star of n, t minus tau is becomes of n, and dt is a dn, modified equation. Okay, R12 of. Also we know that the another equation, R21 of tau, the integral minus infinite to infinite, I'm interchanging the two functions. As x1 you can write as x2, and x2 star it becomes of x1 star t minus tau. Okay. Now let t is equal to n. T is equal to n. You can write it as a t is equal to n. Replace that here. T is equal to n. The t is equal to n, and the t is equal to n minus tau, and the dt is a dn. Now only I am changing the variable t as n. Okay, as a duality property showing that it is a change of t as omega and omega as a t. Now the t I am changing as a n here, the t is n. Now we got the R12 of tau is equal to integral minus infinite to infinite x2 of n, x1 star of n minus tau dn. Now I am taking this conjugate of R12, R21, not the R12, R21 star of tau is equal to x2 of n becomes of x2 star of n, and x1 star is already there, star of star conjugate and conjugate, you will get the real term, x1 of n minus tau dn. Okay, my dear friends. Now R21 star of tau is equal to. Now change the tau as a minus tau now. Change the minus tau. Integral minus infinite to infinite x2 star of n, x1 n minus of minus is becomes is a plus minus, students. So now you can observe the two equations here. R21 star of minus tau is similar to this function, x2 star of n, x1 of n plus tau dn with respect to. So when these two signals are equal, whenever if I am changing the first signal as a second signal and the second signal as a first signal and replacing the tau as a minus tau. Then only the both are equal. Okay, unlike the convolution, the cross correlation is not commutative. So this is a statement we have. Unlike the convolution, the cross correlation is not commutative. So actually, if it is both are equal, R12 of tau and R21 star of minus tau. Okay, after the conjugate and change of minus tau, then only the interchangings both are equal. But R12 of tau is not equal to the R21 of tau. Okay, my dear students. So this is the equation. This is a very important property, my dear students. See, very important property for the both the power signal and the energy signal. So power signal means only simple we can limit t tends to infinite 1 by t, the integral minus t by to the t by 2. The same equation. The same equation. First of all, you can take the t minus tau is a n and apply the derivative dt is equal to dn and replace and interchange the signals x2 as x1 as x2 and x1 as x2 as x1. Let replace the t as n and then conjugate the cross correlation equation R1 to 1 of tau and change the tau as a minus tau. Then only those both are equal. Okay. The R12 of tau is equal to R21 star of minus tau. Then coming to the autocorrelation, my students. Again, the autocorrelation is also having the autocorrelation for energy signals and autocorrelation for the power signal also. See, the autocorrelation function gives the energy of match or similarity or relatedness or the coherence between a signal and its time delayed version. Here also the same, but the signals are not the different signals, the same signals itself we are comparing and see how far it having the similarities or there or relatedness or coherence between the signals and its time delayed version. This means that the autocorrelation function is a special form of cross correlation function. It is defined as a correlation of a signal with itself. A special form of cross correlation function. It is defined as a correlation of a signal with itself only. The autocorrelation is defined separately for energy signals and the power signals. Coming to the energy signal, R11. See here, I wrote here the R11 only with the same signal. R11 of tau is equal to R of tau. So no need to write the 11. You simply write it as R of tau. R12 of tau is a cross correlation denoted as, and autocorrelation is denoted as R11 of tau or 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 R of tau, my dear students. So the integral minus infinite to infinite x of t x star of t minus tau dt. The equation is the same, but here it is not the different signals, it's the same signals. 1 only. No need to replace the x1 of t and x1 star of t minus tau. Okay, where tau is called the time delayed parameter and the signal x of t is shifted by tau samples in the positive direction. If x of t is shifted by tau samples in the negative direction, it is a positive direction, my students. A negative direction means x of t plus tau. X of t plus tau. Take the conjugate of x star of t dt. X star of t dt. Okay. Coming to the properties of autocorrelation function of energy signals, the following properties. Here also, R of tau is equal to R star of minus tau only. The autocorrelation function exhibits conjugate symmetry. conjugate symmetry. We are not saying here it is a commutative property, because commutative property means only obeys for the two different signals. AB is equal to BA. But here, there is no any different signals here, the same signals. The same signals. We are not discussing about the commutative here, autocorrelation function. In the cross correlation only, there is a board we are discussing the commutative. Unlike the convolution, the correlation is not a commutative. But here, don't use that, it is a commutative, because the two signals are the same. Even that, the R of tau is equal to, when it is both are equal, R star of minus tau only. Thus, it states that the real part of R of tau is an even function of tau, and the imaginary part of R of tau is an odd function of the tau. Imaginary we are taking. The real function is R of tau, the conjugate is imaginary. Conjugate nothing but x plus iy. A real term is either it is a x or it is a y. Now see the proof here. The autocorrelation of energy signal is given as R of tau is equal to integral minus infinite to infinite x of t x star of t minus tau dt. The autocorrelation definition. Now I'm taking the conjugate on both sides. R star of tau is equal to, already we have the x of t, that is a conjugate now, and x star of t minus tau dt. Now it is a conjugate of conjugate is equal to the real term x of t minus tau dt. Replace the tau as a minus tau, then it becomes of integral minus infinite to infinite x star of t x of t plus tau dt. It is also equivalent of R of tau only. Okay, it is also equivalent to the R of tau, but in the direction is different. For the negative values of for negative direction, and this one is a positive direction. This is a positive direction. Okay, x star of t is equal to x of t plus tau. This is C. The R of t is equal to R of tau is equal. Sorry, R of tau is equal to integral minus infinite to infinite x star of t x of t plus tau dt. Then R of tau is equal to R star of minus tau. This is the first property. Already we already discussed about in the cross correlation also. R12 of tau is equal to R21 star of minus tau. And second property, in the cross correlation we are saying it is both signals are orthogonal, and the cross correlation is equal to 0 and tau is equal to 0. Now coming to the autocorrelation function, when the tau is equal to 0, the autocorrelation becomes the energy signal. The value of autocorrelation function of energy signal at origin, that is tau is equal to 0, is equal to the total energy of the signal. See, you can take these both equations here. When I am taking the R of tau is equal to integral minus infinite to infinite x of t x star of t minus tau dt. At t is equal, tau is equal to 0, R of 0 is equal to integral minus infinite to infinite x of t x star of t minus tau, t minus 0 dt. That is equal to integral minus infinite to infinite x of t x star of t dt. We know one signal is a real and another signal is a complex, means it's having the magnitude, squared magnitude of x of t, and is equal to the energy signal, my students. Is equal to the energy signal. What is the energy? E is equal to error energy means xc of t. Input energy means ex of. So integral x of t, the squared magnitude of x of t dt. Or otherwise, you can use this equation also. R of tau is equal to, for the negative direction values of tau, integral minus infinite to infinite x of t plus tau x star of t dt is equal to, now the tau is equal to 0 here, r of tau integral minus infinite to infinite x of t when the tau is equal to 0 here into x star of t dt. Now what is the x of t and x star of t? Nothing but the squared magnitude of x of t dt is equal to energy signal. Okay. Autocorrelation function r of tau is equal to energy signal at tau is equal to 0. You can take either it is a direction of positive direction equation or it is a tau is in the negative direction of equation. Both the equations will get the same result. At tau is equal to 0, energy only. Okay, my dear students. That is the second property here saying the value of autocorrelation function of energy signal at origin, that is tau is equal to 0, is equal to the total energy of the signal. R of 0 is equal to E, that is equal to integral minus, not the minus, minus infinite to infinite magnitude of squared magnitude of x of t. So proof here, see, put the tau is equal to 0, x of t and x star of t dt, and x of t and x star of t is the squared magnitude of x of t dt is equal to energy signal. Okay, my dear students. And coming to the third property, this third property is somewhat different, my dear students. You don't have any this type of property in the cross correlation equation. If tau is increased, so listen carefully here, the statement of a third property of autocorrelation function. If tau is increased in either direction, either tau in the negative direction or the tau in the positive direction, the autocorrelation r of tau reduces. If tau is increases, r of tau is reduces. As tau reduces, autocorrelation r of tau increases. Okay, my dear students. As a tau reduces, the autocorrelation function r of tau increases, vice versa. And it is maximum at tau is equal to 0, that is at the origin. Therefore, the magnitude of r of tau is less than or equal to r of 0 for all the values of tau. Okay. You see the tau is increased in either the direction. So you can see the proof here. Consider the function x of t and x of t plus tau, the two different signals. One signal is a delayed version of the other signal, either in the positive direction or in the negative direction. Now I take these two signals added here, x of t plus r minus x of t plus tau whole square is always greater than or equal to the 0 since it is a square. Always greater than or equal to since it is a squared function. So I'm taking the x square of t, expanding this function x square of t plus x square of t plus tau plus or minus 2x of t x of t plus tau is greater than or equal to 0. Is greater than or equal to 0 because of whenever adding in the square is always greater than or equal to the 0. Now again you can simplify here, the x square of t plus x square of t plus tau is greater than or equal to, because it's a plus or minus. Plus is becomes minus and minus is becomes plus when you can shift to the right side. 2x of t, x of t plus tau. Integrate on both sides. The first one is integral minus infinite to infinite. You can take the squared magnitude is z plus integral minus infinite to infinite. For the second one also the squared magnitude of x of t plus tau dt is greater than or equal to integral minus infinite to infinite x of t plus tau dt. So this is also the energy signal, and the second one is also the energy signal, my students. Okay, because at tau is equal to 0, definitely that becomes of the energy signal. So E plus E is equal to greater than or equal to, see, this is the equation of autocorrelation equation. Integral minus infinite x of t plus tau dt for the negative direction of the tau, r of tau. If x of t is a real valued function, x of t is a real valued function. I'm not taking the complex here. Therefore, E plus E is a 2E, and 2 to get cancelled, the energy signal is greater than or equal to r of tau. When the energy signal becomes of 0 at tau is equal to 0, my students. Okay, that energy signal E autocorrelation relation is according to that, at tau is equal to 0, r of 0 is equal to energy signal. E is equal to, here see the second property saying that E is equal to r of 0. When we get the energy signal at tau is equal to 0 only. So I'm replacing the E as r of 0. R of 0 is greater than or equal to magnitude of r of tau, since r of 0 is equal to E. Therefore, r of tau is less than or equal to r of 0. What we are to prove that it is r of tau is less than or equal to r of 0. We got here it is r of 0 is greater than or equal to r of tau, my dear students. It is also very important property. As if tau is increased in either direction, the autocorrelation r of tau reduces. R of tau is less than or equal to, nothing but the tau is reduced. As the tau is reduces, autocorrelation function increases. So vice versa. Okay, and it maximum at the tau is equal to 0 at the origin. Therefore, you can prove that r of tau is less than or equal to r of 0. Following, my students. Then the last property saying that the autocorrelation function r of tau and the energy spectral density function psi of omega. The new word we got here now, my dear students. Till now we discussed about the convolution, correlation, and correlation of the two types, cross correlation and autocorrelation. And cross correlation is denoted as R12 of tau, and autocorrelation is denoted as R of tau. And the cross correlation either in the energy signals and the power signals having properties. And similarly, the autocorrelation is also having represented in the energy signals and the power signals. Now, a new word we got, it is energy spectral density, nothing but the psi of omega, psi. See here, energy spectral density represented as psi of omega. Energy spectral density. Now the power spectral density, S of omega. Remember that. Energy is E, energy signal. Power signal is a P, and the energy spectral density, psi of F, power spectral density, S of F. And now, what is the fourth property saying that there is a relation between of autocorrelation and energy spectral density, psi of omega. What is that relation? Fourier transformation relation. R of tau is a Fourier transformation to the psi of omega. Psi of omega is a frequency domain and is a time domain. R of tau autocorrelation, it is a Fourier transformation relation to the psi of omega, or psi of omega is an inverse Fourier transformation of R of omega. That is nothing but autocorrelation theorem. See here, the autocorrelation theorem. The autocorrelation theorem states that the Fourier transform of autocorrelation function R of tau yields the energy density function of the signal x of t. Energy density function of a signal x of t. Nothing but the psi of omega. Psi of omega. The squared magnitude. The Fourier transformation of R of tau is equal to the squared magnitude of x of omega. That squared magnitude of x of omega, call it as energy spectral density psi of f. So energy signal E is equal to integral minus infinity to infinity the squared magnitude of x of t, my students, into dt. The psi of f is, what is the psi of f? Not the psi of f, sorry, psi of omega. F is also the same thing only. Psi of f or the psi of omega. It's a normal frequency, it's angular frequency we are taking. It is not in the time domain, energy spectral density, the frequency domain. The psi of omega is equal to frequency domain. This is squared magnitude of x of omega. With respect to the d omega here, the Parseval's theorem, you know, integral minus infinity to infinity as a Parseval's theorem. Now, we go for the proof of autocorrelation theorem to prove R of tau related to the psi of omega. So R of tau, the Fourier transformation, you take the Fourier transformation equation, integral minus infinity to infinity R of tau e power minus j omega tau d tau. What is R of tau? Autocorrelation equation, the x of t minus tau integral minus infinity infinity into dt, my dear students here. Okay, I will explain here. So the Fourier transformation of R of tau, now to prove that it is a energy spectral density psi of f. What is a Fourier transformation definition? Integral minus infinity to infinity. I'm taking the R of tau as a signal, input signal. R of tau e power minus j omega t. Actually, it is a t, my dear students, but here the tau is there. So you write it as a e power minus j omega tau, and it is also with respect to the t. But here, the tau I am taking R of tau e power minus j omega tau d tau. Is a Fourier transformation of autocorrelation is equal to integral minus infinity to infinity. What is R of tau? According to the definition of autocorrelation function, integral minus infinity to infinity x of t minus tau dt. Okay. For the positive direction of tau values, and e power minus j omega tau d tau from the definition of Fourier transformation. Okay, my dear friends, is equal to, now rewrite this function as a t terms and the tau terms is separately, integral minus infinity to infinity, integral minus infinity to infinity x of t e power minus j omega t. I am writing here. There is no any t term is there. Now add, multiply the e power plus j omega t and e power minus j omega t in this function. And take the e power minus j omega t dt. Okay, my dear students. There is no any e power minus j omega t in the above equation. Now I'm multiplying the e power minus j omega t. So again, you can multiply the e power plus j omega t. It satisfies, there is no any change in the previous equation, the present equation. And other integral is there, e power minus infinity to infinity. I'm taking the another signal, the delayed signal x of t minus tau e power j omega tau. Already we have the e power minus j omega tau. I'm adding, not the adding, sorry, multiplying the e power j omega t e power minus j omega tau d tau. Okay. So now see, here the plus and here the minus. The present equation, the previous equations, both are the same. The integral minus infinity to infinity. X of t e power minus j omega t dt is nothing but is x of omega minus students. X of omega as a Fourier transformation definition. And another equation, integral minus infinity to infinity. X of t minus tau e power. Now the basis of the same, we can add the power j omega into t minus tau d tau. Already the dt here, and it is a d tau, my students. D tau. X of t minus tau e power minus j omega t minus tau the d tau. Okay. Here the delayed of the samples, and e power minus j is also delayed here. The same thing. Now the x of omega, it is also same value, the x of omega, or if it is a conjugate, you can take with the delayed version x of t minus tau and e power j omega the t minus tau. As of the Fourier transformation relation, or the relation, the definition, e power x of t e power j omega t dt. What is the t here? The t minus tau and j omega t minus tau and the d tau. But somewhat it is a difficult to write these x as x of t minus tau and the j omega t minus tau the dt as a Fourier transformation relation. Change the t minus tau is equal to n. Let the t minus tau is equal to n in the second integral. We have it becomes of a Fourier transformation relation of x of omega. Okay, let the t minus tau. It is also equal to the x of omega actually. Now, the t minus tau, we write it as n, and the t is equal to n plus tau. N plus tau minus plus. Okay. Now the x of omega into the integral minus infinite to infinite, x of t minus tau becomes x of n, and e power j omega t minus tau is a n here, and d tau. What is the d tau? Apply the derivative on both sides. Apply the derivative on both sides. D tau is equal to dn. D tau I am taking here dn, but with a minus omega, because it's a minus is there, minus tau, and n is equal to. When I'm changing this as a minus a d tau and is equal to dn, the t is a constant. T is equal to. So replace the my d tau is a minus d tau. It is a d tau is equal to minus dn, or otherwise it changes x of minus omega. X of minus omega. Why it is the minus of the omega is changes, the minus will get with respect to the x of omega is equal to integral minus infinite to infinite. It becomes of x of n e power j omega n and dn as a minus. Here it is a minus students. Whenever it is the e power j omega n is a positive value here, is a positive value. It change this as replacing the x as a minus omega according to the duality property. When using the duality property, x of minus n and the x of minus j omega and dn, this becomes of x of omega into x of minus omega. X of omega into x of minus omega. It's a complex, or it is a star, the function. You can take it as a star function, the x of omega and the x star of omega, by changing of omega as a plus. Okay, e power j value, the omega is becomes of when is a positive whenever if you take the conjugate value. So x of omega and x star of omega becomes the squared magnitude of x of omega is nothing but psi of omega, energy spectral density. So the Fourier transformation R of omega is equal to x of omega integral minus infinite to infinite x of n e power j omega n and the dn. J omega n, the dn value. So whenever if you can take the minus x of minus omega, then only it is a Fourier transformation relation. So x of omega and x of minus omega or x star of omega, it becomes of the squared magnitude of x of omega is equal to psi of omega, energy spectral density. Now the relation between of autocorrelation and the energy spectral density is Fourier transformation relation, psi of omega. Okay. And the next one is autocorrelation function for power periodic signals. Power periodic signals. Only with respect to the time, not with respect to the time, my students, is the periodic function. The power is nothing but the periodic. Periodic means having a interval or up to the value of the t, and it is repeated with that interval, specified interval. We can call it as a periodic signal. It is a period of the t. Limit t tends to infinite 1 by the integral minus t by the t by 2 x of t x star of t minus tau dt, or x of t plus tau x star of t dt. Now the properties of autocorrelation for the power signals. R of tau is equal to R star of minus tau. The same thing what we have in the energy signal also. Autocorrelation. You see the R of tau is a limit t tends to infinite 1 by t. X of t x star of t minus tau dt. And take the conjugate on both sides. X star of x of t minus tau dt. And change tau as minus tau. Limit t tends to infinite 1 by t the integral minus t by the t by 2. X star of t x of t plus tau dt is also equal to the autocorrelation only. So R star of minus tau is equal to R of. Okay. Second property, the autocorrelation function at origin is equal to the average power of the signal. The autocorrelation function at origin means the tau is equal to 0. The tau is equal to 0, it becomes of x of t x star of t. So limit t tends to infinite 1 by t the integral minus t by the t by 2 squared magnitude of x of t dt is equal to the power signal. And third property, already we proved that in the energy signal, the R of tau is less than or equal to R of 0. As the autocorrelation tau is increases, autocorrelation function is decreases. Or the tau is reduces, the autocorrelation function is increases. So R of tau is less than or equal to R of 0. R of 0 is greater than or equal to R of tau. The value of autocorrelation reduces as tau increases from origin. Reduces as the tau increases from origin. And the fourth property, R of tau is a Fourier transformation relation for the power spectral density. In energy, we have energy spectral density Fourier transformation. Now the autocorrelation function is also related to the Fourier transformation for power spectral density S of omega. S of omega. Power spectral density forms a Fourier transformation pair. Since it is a periodic signal, the power is a periodic signal. The another property we have, the autocorrelation function is a periodic with the same period as periodic signal itself. You know, the periodic signal means x of t is equal to x of t plus t as a continuous time function, or x of n is equal to x of n plus capital N, where n is a fundamental period or t is also the fundamental period. Similar way, the autocorrelation function is a periodic. What is the autocorrelation function? R of tau is equal to R of tau plus R minus n into t, because it's a continuous time function. R of tau plus t actually, either it is an increasing of with the multiplication factor of n into capital T, either it is a plus or minus. The autocorrelation function is periodic with the period as a periodic signal itself. R of tau is equal to R of tau plus R minus n into t where n is equal to 1, 2, 3, and so on. Okay. We already discussed about the properties of autocorrelation function for energy signals and autocorrelation function for periodic signals. Now, what is the energy density spectrum? What is a spectral density? Energy power spectral density. Energy density spectrum or the spectral density. Spectral density, it is a distribution of energy or power of a signal. It is a distribution of energy or power of a signal per unit bandwidth as a function of a frequency for energy signals and the normalized energy signals. See, we already know in the energy and the power signals in the Fourier transformation classification we've seen. We already discussed that when energy is in between the range of 0 to infinite, the power is a 0. When it is an energy signal, the signal with finite energy and the 0 average power. When we can say it is energy signal, the signal with finite energy means in between of 0 to infinite, it is not equal to. It is in energy signal is greater than the 0 and less than the infinite. The signal with finite energy and 0 average power is called energy signals. Example, aperiodic signals like pulse. Aperiodic or the non-periodic signals like pulse. When we can say it is energy signals means, my dear students, the signal with finite energy and 0 average power. The 0 less than energy less than infinite and the P is equal to 0, we call it as energy signals. The normalized energy or simply energy of a signal x of t is defined the energy dissipated by the voltage applied across 1 ohms resistance or by current signal flowing through the 1 ohms resistor mathematically. So forget about these, all the things matters. Normalized energy signal E is equal to integral minus infinite x square of t dt. I'm taking the magnitude, the squared magnitude of x of t dt. The energy of a signal exists only if E is finite. The energy signal exists. Remember, my dear students, it's a very important point. The energy of a signal exists only if E is finite. That is only if 0 less than E less than infinite. Okay. Previously, I told that the squared magnitude of x of omega, the energy is equal. You can call it as by the Parseval's theorem, or it is a Rayleigh's energy theorem. Parseval's theorem for the energy signal. We did in the one of the property of Fourier transformation, my students. The E is equal to squared magnitude of x of t whole square dt is equal to 1 by 2 pi integral minus infinite or the squared magnitude of x of f d omega, or it is also equal to the integral minus infinite squared magnitude of x of f into df as by using the Parseval's theorem. Okay. Proof. Consider the function x of t such that x of t is x of omega. X star of omega means x star of t and x star of minus omega, my students. The relation of Fourier transformation. X star of t, the conjugate of time domain function, is also in the frequency domain is conjugate, but the omega is a negative of minus omega. The energy of or a signal x of t is given as E is equal to this function. The squared magnitude you can write as x of t, x star of t. Okay. Or integral minus infinite x star of t, x of t dt. Replacing x of t by its inverse Fourier transformation. X of t. What is the inverse Fourier transformation formula? 1 by 2 pi integral minus infinite x of omega e power j omega t d omega into dt. Okay, E is equal to 1 by 2 pi x of omega and integral minus infinity x star of t e power j omega t dt and d omega. So within the parentheses we can see there is x star and e power j omega t dt. I'm changing the star whole star here and keep the positive exponential is a negative exponential. X of omega and x star of omega minus we will get here, my students. X of omega, x star of minus omega. Because the star x star of omega is a x star of minus omega. That is equal to 1 by 2 pi the integral minus infinite x of omega whole square. Okay, there's a little bit confusion we'll get, my students. How it is changes integral minus infinite x star of t e power j omega t dt. Now I'm taking the whole star here, whole star conjugate. I'm replacing the conjugate value. Integral minus infinite x star of t is t e power minus j omega t dt. So again, this function is x of omega 1, x of omega star. So x of omega, x star of omega is the square magnitude of x of omega d omega. Okay, and omega is equal to 2 pi f, d omega is equal to 2 pi into df. The 2 pi get cancelled. Energy E is equal to integral minus infinite squared magnitude of x of f into df. This is called Parseval's theorem for energy signals, also called as Rayleigh's energy theorem. Rayleigh's energy theorem. Okay, my dear students. So the tomorrow class can go for the discussion about the remaining topics. Energy density spectrum, and then it is a power spectrum density also. Power density spectrum. Energy spectral density and power spectral density. Power density spectrum and some of the proofs and power spectral density. Okay. Tomorrow class we can discuss the remaining topics, my dear students. Any doubts? So first time when we listen the video in the YouTube, my dear students, it is somewhat difficult to understand. 2-3 times we can refer the books, or 2-3 times you can listen the video, then only you can understand this chapter, my dear students. So what is the energy signals and what is the power signals and what is a correlation function and what is the different types of correlations, cross correlation and autocorrelation, what are the properties of autocorrelation and what are the properties of cross correlation, and what is the relation between of energy and energy spectral density and power spectral density. So first time it is somewhat difficult, my dear student. Definitely you get the confusion. Okay, you write down 2-3 times each one, then listen twice, then only you can understand, my dear students. Okay, at first time don't think that it's a very difficult. After the listening of the first time only, don't get into that. It is very, very difficult. 2-3 times you can listen, and 2 or 3 times you have to write down all the properties. Then you can get some idea and in the easy way. Okay, my dear students. Any questions? Thank you.